Hello guys, welcome to another video from Counterexample channel. In this video we're gonna solve the question number 15 from Sipser textbook, and actually this question is about another fact in NFAs, and we want to actually use from a new method to construct an NFA for languages that we want to show them with a star operation. And actually somehow we show that with one counterexample that this method is wrong and we can't use from this method. And yes, that's it. I hope you guys enjoyed this video and let's solve it together. Okay guys, this is the question form that we have here. Give a counterexample to show that the following construction fails to prove the theorem 1.49, the closure of the class of regular languages under the star operation. Let n1 is equal to q1 and sigma, actually delta 1, q1 and f1 recognizes a1, construct n with q1 sigma delta q1 and f as follows. N is supposed to recognize a1 star. The first part in this question says that the state of n are the state of n1, the exact state of n1. So this part is actually we can see this part in both NFA that we have here. The second part says that the start state of n is the same as the start state of n1. So yes, this part is same. And the third part says that f is equal to the union of q1 and f1. And actually we have the problem with this part here that says that our exact state is the union of q1 and f1, and we want to show that with one counterexample that this part makes some mistakes and this part is wrong. And the final part is exactly like the same method that we have for constructing the NFA for a star operation. First, let me show you the theorem 1.49. This is the theorem that we have here. The class of regular languages is closed under the star operation. The method that we use here is that if we have a NFA, all we have to do is that we actually define a new start state, actually like this, and this new start state become one of our acceptable states in new NFA that we have for a star operation, and we define a new arrow to our old start state, that is this part, and yes, here. And in this arrow we have the epsilon transition for this transition that we have here, and we add some arrows from our old acceptable state like this and this to our old starter state like these arrows. And also these arrows that we define contains epsilon transition. This is the old method that we have here, but in this new method that the book suggests here, all we have to do, assume that we have this NFA here, actually like this A and B, and these are our acceptable states. All we have to do is that define these new arrows to our old starter state with epsilon, and this our old starter state become one of our acceptable state. And in this new method we don't need to define one new starter state and actually transform it to one of our acceptable state, and we want to show that this method here is wrong. So let me show you with one example. Assume that we want to construct a DFA for, actually, better I say, this language here. We have 1 a star, after that 0. Yes, this is okay. If you want to construct a DFA for this language here, or better I say construct an NFA for this, it will become like this. We have Q0 here. We must have the even number of ones, so it will become like this. We have Q1 here, and with this we will back to our Q0. This is for that we want to recognize even number of ones, and after that, if we see a zero actually here, we will reach our acceptable state Q2. So yes, this is the NFA for this language here. If we use from this new method here, our actually new NFA for LSR will become like this. So LSR is something like this. We have 1 star, and after that 0 in a big star here, and our new actually NFA will become something like this. We have Q0 again, and after that some arrows to Q1 for recognizing the even number of ones. So it will become like this. Yes, and after that we have a final arrow for recognizing 0 to Q2, and actually this is one of our acceptable state, and all we have to do is that we add one arrows here with epsilon on it to our Q0, or better I say old started state, and this started state will become one of our acceptable states. So yes, this is the NFA that we can construct with this new method here. But actually we have some mistake here, because in our old NFA we know that we can't accept some string actually like epsilon, sorry, better I say 1. Here we can't accept this string here, but if we use from this new method, we will go to our NFA here with this arrow, and after that, let me show you with red color, we will continue with 1 here, and after that another 1 to here, and we will reach our new acceptable state here, that is actually not one of our string in our language, because if you see our language here, we can accept 110 or maybe 11110, but in any of our string that we have here, we can't accept 1.1, and this is a big mistake that we have here, and this is the example that you can use to show that this new method, if you want to use it, is wrong. And yes, this is the solution for this question, and I hope you guys enjoyed this video and learn a lot of things about NFA here. If you like it, you can like my video and subscribe to my channel. This is a big motive for me, and if you have any idea or opinion, you can leave them in comments part. I will read all of your comments, and again, this is a big motive for me. And finally, if you really love my channel, you can subscribe to my channel. And yes, that's it. Have a nice day, guys. Goodbye.